Greetings, folks. Today we're going to talk about Cascode Amplifier. What's Cascode Amplifier? What's the point? Well, the Cascode Amplifier is essentially a two-transistor circuit. You could use two FETs. You could use two bipolars. They share a bias configuration, and I'll explain that in just a sec. But the whole point of it is to reduce the Miller effect on the feedback capacitor. In other words, the capacitor that's sitting from drain to gate, or in a bipolar from collector to base. All right? By reducing that capacitance, the input lag network, that critical frequency can be increased considerably. So this is especially useful if you have a large impedance in the signal source, in the generator. That's going to be a huge advantage to have a decreased capacitance. Now, you'll sometimes hear people say that cascode amplifiers eliminate the Miller effect. They don't completely eliminate it, but done properly, it is reduced by a considerable amount. This configuration using two transistors uses far fewer components than if you just created a two-stage amplifier. So you're going to wind up with a large input impedance, and you're also going to end up with a good F2 out of the system if done correctly. So the first of these two transistor stages effectively is a common emitter or a common source if you're using a FET. And that feeds the second stage, which is a common base if it's a bipolar, or a common gate, right? If it's a JFET. Now the way this is configured, that very first stage, and I'm going to use stage in quotes here because it's not like a normal, capacitively coupled stage that you would see. That first common emitter, common source section, let's call it that, would have a gain of 1. It's an inverting gain, but it's a gain of unity, and it will have a high input impedance. The following transistor, configured as common base or common gate, will produce most of your voltage gain. Right? So you might get a gate of 5 or 10 or 20 or, whatever the heck it's set up to be. Now, the bigger the gain on that second stage, the greater the advantage over a single stage common emitter or common source amplifier that's going to suffer from Miller effect. And if you're saying, hey, I forgot about Miller effect, what is that? Well, Miller effect for capacitors looks like this. We start off with an amplifier, an inverting amplifier. If there is a component bridging that in this sort of feedback position from input to output, we can make an equivalence of this, which is that same amplifier, but the cap in two pieces, an input Miller capacitance and an output Miller capacitance. Now, the general case of Miller's theorem for an impedance is that it will lower the value, the feedback value for the input and the output Miller equivalences. Because capacitive reactance behaves inversely to capacitance, then we find effectively a multiplication of the feedback cap. So the input Miller cap would be the feedback cap times the gain plus 1, and this is the gain magnitude, right? So if you have a gain of negative 10, you're multiplying this by 10 plus 1, or 11. And on the output end, it's C times the quantity A plus 1 over A. So we have a modest increase at the output, but there's a huge input Miller capacitance that we see. Right? So this is what's really going to hurt you. Now, if we go over to a fairly standard, say, common source amplifier, I'm going to do this whole thing with JFETs. So we've seen something like this before. If it's not familiar, pick up the Semiconductor Devices book. Again, free download if you don't have it. Just look in the description of the video, and there's directions and where to obtain it. Or you can go back and look at the other videos in this playlist that talk about the either the JFET amplifier, or there are some other ones on lag network response. So if you haven't seen those yet, I strongly suggest you take a look at those first. But in any case, here we have a little self-biased JFET, right? So there's really two caps to concern ourselves with, and that would be the drain to gate capacitance and the gate to source capacitance. So this gate to drain capacitance is in that feedback position. This is going to get multiplied up by the gain and appear out here. Now I've shown this with a fairly large source impedance, right? So I've got a 5K ohm source impedance back here. Generator impedance, let's use that since there's a FET source. I don't want to confuse those two things, right? So let's just call that the generator impedance. And you might have a passive device, for example, that has a fairly high output resistance, in this case 5K. So coupled with this sort of multiplied capacitance, the lag frequency, the critical frequency on the input network is really going to suffer. All right, so I've done some preliminary calculations on this particular circuit, right? Remember the gain of a circuit like this, common source amplifier, is a negative GM times RD, where RD is the AC drain resistance, where we have the bias resistance, in this case 6K, in parallel with the load of 12K. So 6 in parallel of 12, you're going to get 4K for that, all right? So you find out what the GM is, and the way this is biased up, like I said, with the self-bias. And there is a video specifically on using the self-bias. So again, check that out. I'm not going to go through all the details on this, but it does work out that we get a GM of about 4.4 millisiemens. And with this effective 4K AC drain resistance, we get an inverting gain of about 17.6 out of this. Now, off the data sheet, we pull off the values for the two capacitors, which are 2.2 picofarads, as the old timers would say, puff, 2.2 puff, from drain to gate right here, and another 4 picofarads from gate to source. Okay? Now it's important, this is important as we're going to see in a sec, drain to source DC bias voltage is approximately 10 volts in this circuit. So we're going to use a curve, right? Just don't grab the data sheet and grab a max or a typical value. You want a little bit more accuracy, get the curve for the capacitances and look up the appropriate reverse bias potential. So I've already done that. In any case, we've got a little over 2 pico and about 4 pico for the gate source. All right. So we could immediately come in here and do maybe a quick DC analysis just to show that everything is right. And I'm going to do this. So if you're building this on your own, right, you're going to build this circuit on your own. You just want to do some cross-checking just to make sure you have the same stuff, right? Your gate over here should be approximately 0. We're getting 24 microvolts. The FET source is coming in at 1.689 volts. And that's actually giving us a little under a milliamp, 0.844 milliamps, 844 microamps. And importantly, as I said, the DC drain voltage is coming in at just under 10 volts. All right, so like I said, you can use that for comparative purposes. Now we can run a simulation and see what we get. But before we do that, I've done the calculations for what we expect to see. So on the input end, right, our resistance would be the Z into gate, which would be infinity, in parallel with the 2 meg biasing resistor, in parallel with the 5K generator impedance. Remember, the generator shorts out. Caps are sitting out here, so all those resistors look like they are in parallel from the position of the lag capacitor. C2, of course, is treated as a short, as is C3, as is C4. Okay, so the total lag capacitance that you see is the gate source capacitance, like I said, 4 pico, plus the Miller. So here's where you're getting really shot down here. We've got a gain of 17.6, so A plus 1 is 18.6 times the capacitance that you see from gate to drain, 2.2. So you add that all up and you get nearly 45 picofarads. So you take that 45 picofarads, 5K, use your universal critical frequency formula, 1 over 2 pi RC, and we get 709 kilohertz. All right, so that's what we're expecting to see there. A little side note, the data sheet that I used for this particular FET, the graph was, let's say, less than perfect. There was a little bit of an ambiguity in the reading of the graph. So there was another way to interpret the capacitance from the gate to drain, from the gate to source, which slightly altered the total capacitance and the frequency. In fact, that one came out to 658 kilohertz. So either way, we're looking at the better part of 1 megahertz, about 2/3 of a meg, let's call it that, okay? Split the difference. On the output end, again, C3 is a short, R5 and R4, the bias and the load, 6 in parallel 12 is 4K, and we'll just ignore the internal impedance of the current source, the controlled current source for the JFET, all right? The output capacitance will be the Millerized drain to gate capacitance, so that's A plus 1 over A times the capacitance, and that works out to 2 1/3 picofarads. You grind that through and you get 17.1 megahertz. So clearly the input network is the critical frequency, is the dominant network. It is establishing the critical frequency for the amplifier. So let's run an AC analysis and see what we get. Alrighty, let's bring this down here. Let's expand this a little bit. All right, so let's check the gain. And we had 17.6, which in decibels is 24.9, and we're getting 24.92, right? The real question is, where's the critical frequency, right? So it's going to be 3 decibels down from that, looking at F2, which would be 21.9. So I'm just going to swing this over to 21.9, as close as I can get to it. All right. And so we're sitting at about, well, that's not quite. Let's see if I can, what are we getting? 620. So let's just call that 628. Okay. That's, I think, close enough. 628 kilohertz. So we're a little shy of what the calculation is, but not too bad. All right, that's not too bad. There might be a little bit of interaction between these, but this is more than a decade, so I don't expect too much. I'm going to guess most of that is just, from the model that we're using, how accurate are these, reading these things. Then there's the question of, how much of an impact did ignoring that internal current source have, But we're certainly within the ballpark, right? We're looking pretty good. We're within, a few percentage points anyway. All right, so that's our base, right? This is our sort of base level. Now I want to improve this with this Cascode. You've been talking about Cascode. Let's see an actual Cascode amplifier. Okay, so Cascode version of this. As it turns out, we're only going to add 1 FET and a DC power source, and that's it. And here it is. Bonk. Okay, so the upper end, now I've changed the VDD supply, and I'll explain that in a sec, but here's our 6K biasing resistor, the 12K load, the output cap, that FET, all right? Let me just go back, and you can look at that upper section. Oops. Look at that upper section, and you can see that it is the same, right? We have these same components. Now look at the bottom section. I'm basically going to split this FET into 2 FETs is really what it boils down to. So I got this 2 meg and 2K and the 470. All right, so you still have those, 2 meg, 2K, 470. Still have the same thing on the input. I've got the generator impedance of 5K and the 100 nanofarad cap. Just kind of ignore this for just a sec. And we just have T1 and T2. Right? So really it's like I just took that 1 FET, turned it into 2 FETs, and then I added a power supply over here on the base, on the gate of this second FET. All right, so a couple of questions pop up. What the heck is this mess out here called Vout CS? Well, this is because I want to check what the gain out of this first transistor is. So right now I don't need to worry about that. What's with the weird power supplies? Well, as I said before, the bias setup, the DC bias setup, helps establish what these capacitor values are. All right, so we want to keep those the same. So what I've done here, we verified that we had about 10 volts DC sitting on the drain. So I want to do the same thing here. I want to get 10 volts on this drain. I want to get a 10 volt differential, not 10 volts with respect to ground, but a 10 volt differential between drain and gate over here as well. So I've just sort of monkeyed with the power supplies a little bit to get those values, right? And I'll prove that to you. So that was just a little bit of trial and error, you know. I mean, you could make some quick approximations and then you just sort of empirically sort of futz around with them and see what you get, right? So again, there was that 1.6 and change. You know, the current we had was 844. So there it is again, 844 microamps. That's looking good. Sitting off the drain, yeah, we said we had about 10 volts, so we're at 9.99 basically. If I come up to the second drain, the upper drain, that's 18.2, and I've got an 8.3. So that's about 9.9 volts there. So we're very, very close, right? That setup is all very close. All right, so having done that, I've done some basic calculations, and it should turn out that the gain through here is unity, and then the gain from here out to this load, V load, is approximately 18.2, or about 25.25 dB, as it turns out. So what's the deal here? Why the gain of 1? What's happening? Well, again, this FET being operated in a common source configuration, the gain is negative GM times RD. Well, what's RD? Like I said, ignore this. As a matter of fact, it's big enough that you will be able to ignore it. RD is actually the input impedance looking into the source of the upper FET. What is that? Well, this is essentially being operated as a common gate. You know, for AC, this is a short, right? So your AC ground is right here, right there. So the input impedance looking into the source of a common gate configuration JFET is 1 over GM. So think about that for a second. If RD is 1 over GM and the gain of this lower FET is GM times RD, in other words, you're saying it's GM times 1 over GM, which is GM over GM, which is 1. These two things are biased at the same point, right? They're identical FETs. They share the same current, right? This drain current is this source current, and this source current is this drain current, which is this source current. So they have the same currents. They're going to have the same VGS values. We've set it up so that they have the same VDG values. So they should have the same transconductance values. And therefore you get this gain of 1, right? So this common gate configuration is non-inverting. This is the key. This is non-inverting, so there's no Miller effect. When I figure out the output critical frequency, we have the 6K and the 12K, right, 4K, and we have virtually the same capacitance we had before, which is just going to be the gate drain. So in this case, it's the gate drain. In the preceding case, it was the Millerized gate drain, but that's increased by a very small amount, right? It's increased by only a few percent because it's multiplied by gain plus 1 over gain. So not much change, right? There's a very subtle change, but you're going to find that the calculation for the output critical frequency here is very, very close to what it was in the original circuit. But when we look at this circuit down here, the gain here is only 1. So the Miller multiplication factor is A plus 1, in other words, 2. So that multiplication factor is only 2 instead of nearly 20 like it was last time. So that is going to mean that the total input capacitance is going to drop by nearly a factor of 10, which is going to increase that input critical frequency by a considerable amount. It won't be exactly 10, you know, but it's going to be a lot, right? It's going to increase by a factor of like 6 or something like that, whatever it works out to. All right. Now notice that the complexity of this circuit is not much greater than the original, right? It's taller. You got an extra FET, and you have this extra power supply, which in all honesty, you would probably create off of this power supply through a voltage divider, right? You'd have a couple of resistors. You'd tap the gate in between to get the 8.3 volts that you need. And then you'd throw a bypass cap on there because you want to keep this gate at AC ground, right? Otherwise, the high frequency performance might suffer. Okay. There is also an interstage lag network. In other words, between these two, just like when you had two normal capacitively coupled stages, there's an interstage lag network. There's one for this as well. But this is not going to be a problem because, again, the impedances are really small. Again, you're looking at the input impedance of this source, which is 1 over GM. That's, in this case, going to be a little over 200 ohms, right? 1 over the GM. There's your GM right there, 4.5 millisiemens. So that's not going to be very high, and the associated capacitances are also quite low. So that is no way going to be the dominant network. All right, so what I want to do here is, again, we'll look at an AC analysis. I want to check that V out CS is in fact a gain of 1, as we're predicting. All right. Boink. Okay, so let's get our legend out here. All right, so the common source output is the maroon. Here's 0 dB. You can see that's just a tiny smidgen above the 0 dB. All right. Now you want to prove it here. And I'll bring him down a little bit. All right, so it should be ideally 0, and we're getting, 270 some odd milli dB, right? We're getting less than 0.3 dB. So it's a smidge more than 1. For all practical intents and purposes, it's 1. All right, now the main output is sitting here at 25, just about 25 and a quarter, basically. Okay, so 25 and a quarter minus 3 dB is going to be 22 and a quarter. Yoink. Right around there. So we're getting about 3.4 megahertz on this one. All right, 3.4 megahertz. And we were getting like 629 kilohertz for the other one. All right, so that's a considerable increase. Now, how does that compare with our, with our calculation? Well, of course, I've done the calculations ahead of time. So the input network, right, 5K, you've got your CGS, which was 4 picofarads from our data sheet, 2.2 for the gate drain, and here's the kicker, right? Here's the Miller effect, which is only a factor of 2. Okay, A plus 1 over A. A is 1, so it's 2 over 1. So you only get 8.4 picofarads over there instead of, we had 45 or something like that. I forget. Let's see. Let me see if I can go back and look at that. Well, yeah, 44.9. Okay, and we had calculated 709. And we actually measured in the simulator, like I said, 650 or 630, something like that. Okay, so anyway, continuing along. So that works out to 3.79 megahertz versus our simulated 3.4. And again, it's the usual sort of things that could roll into that and create a little bit of deviation. The output network, as I said, we have this output value out here, just again about 2.3 picofarads. It hasn't changed much. It was around 17 megahertz before. All right, 17.1 either way, so there's really no change there. We do have to add in this mid stage. This didn't exist on the other one. So the input resistance is, like I said, the RN source, which is 1 over GM, 213 ohms. Throw in the capacitors, which are fairly small, and this is, of the 3, the highest. It works out to nearly 63 megahertz. Okay, so you're not really going to see much effect on this. Now, these two are close enough that this might explain some of the deviation. When we simulated and we got 3.4 megahertz, this is not a decade away, right? This is actually less than a factor of 5. It's only a couple of octaves away. So that might be one of the reasons why our simulated value is a little bit low, right? We're assuming that these are like, perfect kind of Bode plot things. But we do know, in fact, that at 3.79 megahertz, there isn't 0 loss on the output network. There's going to be some fraction of a dB in there, and consequently, the simulation is going to show up as being a little bit shy, a little bit low compared to what this idealized calculation is. Right? So that doesn't look too crazy. All right, so I think the best way to really focus in on this is to look at both of these things simultaneously. So I've basically pasted the two of these things together in the simulator. I've gotten rid of that pesky little common source output. So I only have 2 outputs, right? I've got the V-load, which is the Cascode output, and V-load 2, which is the original common source amplifier. So we'll go in and do an analysis, write a Bode plot on this. Boom. There we go. All right, so V load 2 is the maroon on the bottom. Look at this. This is crazy, right? Well, it's not crazy, but you look at it and you go, that's fairly impressive. We did as good as we could without going crazy trying to match these things up. I mean, they are only like about 1/3 of a decibel apart. So the two are nicely matched. I mean, it wouldn't be fair, right? If we didn't take care on these power supplies and so forth to get everything matched up nice. So we try to do the best we can there, right? So it's not perfect, but it's pretty darn close. But it's very apparent what you're getting as far as breakpoints. Your 3 dB down is somewhere around here, right? Because this is 20, 25, so 22-ish is around here somewhere. So you're getting this several hundred kilohertz on this one, and you're getting a few megahertz, right? Because there's 2, 3, 4 megahertz for this one, right? So just to be complete about it, right? There's our 25 1/4. So we're going to look for 22 1/4, close as we can get. And on our original circuit, so 24.9, 21.9. Right about there. Okay, so 3.4 meg, 628K. That's a pretty sizable change. Now, a thing to remember is this change, how big this change is really a function of how much gain you have. These are JFETs. We're not getting tons of gain. We're only getting a gain in the upper teens. If you had a bipolar, and you would do the same kind of thing with the bipolar, again, you'd have to monkey with this to set up the bias, but it'd be a similar sort of situation with the two transistors stacked. You could get a lot more gain out of the bipolar. So the advantage that you have in terms of reducing that Miller effect is that much greater. So the Cascode might have an advantage of, a factor of 20 or something, who knows? All depends on the exact values. All right, but this does work well with these FETs if you have a high generator impedance, a signal source impedance, because that is unfortunately going to drive down that input critical frequency, right? That lag frequency. All right, so there we go. Nice JFET Cascode Amplifier answers all the problems that we started with, right? With a modest increase in complexity. One extra FET, a little bit of monkeying around here with a second power supply. Like I said, a couple of resistors for a divider and a bypass cap, and you're good to go. All right, cool. Any questions? You know what to do. Leave them in the comments. Have a good one. We'll see you later.